5 of the most important symbols in mathematics came from 5 different worlds. 0 came from the need to mark nothing. 1 came from counting. Pi came from circles. E came from growth. I came from the uneasy act of taking the square root of a negative number. For centuries, these were not neighbors. They were not even from the same neighborhood. Then Euler found the bridge. E to the I pi plus 1 equals 0. Here, E is the base of natural logarithms. I is the imaginary unit, the square root of -1. Pi is the circle constant. 1 is the multiplicative identity. 0 is the additive identity. The equation looks almost too clean. It has no measurement. It has no physical constant. It has no hidden table of data. It just says that 5 mathematical strangers can lock into one perfect sentence. Richard Feynman called it one of the most remarkable formulas in mathematics. The deeper reason is not that it is pretty. The deeper reason is that it shows a secret. Exponential growth and circular motion are the same machine, seen from two sides. The identity itself does not power modern technology. The broader formula behind it does. E to the ix equals cosine of x plus I sine of x. Here, E is the base of natural logarithms. I is the imaginary unit. X is the angle or input value. Cosine of x is the horizontal part of the motion. Sine of x is the vertical part of the motion. That line sits under Fourier transforms. It sits under signal processing. It sits under alternating current power. It sits under wireless links. It sits under quantum phase. It sits under audio compression. It sits under image compression. It sits under almost every tool that turns waves into something we can compute. This is about the moment the 5 strangers snap together. Imagine walking into a room with 5 symbols on a blackboard: 0, 1, pi, e, I. At first, they look like pieces in a museum case. Each one has its own past. 0 marks absence. It lets arithmetic keep a place for nothing. 1 is the unit. It is one thing. It is one step. It is the number that leaves multiplication unchanged. Pi is geometry packed into a number. Every circle, large or small, carries pi in the ratio of its rim to its width. E is growth in its pure form. When a thing grows at a rate equal to its size, E appears on its own. I is the square root of -1. It starts as a problem. No ordinary real number can square itself and become negative. These 5 constants seem to live in separate kingdoms. Arithmetic has its own ground. Geometry has its own shapes. Analysis has its own tools. Algebra has its own rules. So the puzzle is plain. Why should they ever share one sentence? Not in a long theorem, not in a rough estimate, not in a neat engineering trick. One sentence: E to the I pi plus 1 equals 0. Euler wrote in the 18th century. The modern idea of a function was still taking shape. In 1748, he published Introductio in Analysin Infinitorum. In that book, he helped pull functions, exponentials, logarithms, trigonometric series, and infinite processes into one language. That is the move to remember. Euler was not dressing mathematics with ornaments. He was building a translation system. Before that translation, circular motion belonged to trigonometry. Growth belonged to exponentials. Imaginary numbers were allowed, but with doubt. People could use them in algebra. They struggled to picture them. Then the complex plane gave imaginary numbers a stage. On that stage, a number has 2 coordinates. The horizontal direction is real. The vertical direction is imaginary. A point like 3 plus 2i means 3 steps right and 2 steps up. Now, multiplication is not just scaling. Multiplication can turn. That is the key idea. The imaginary unit, I, acts like a quarter turn. Multiply by I once, you turn 90 degrees. Multiply by I twice, you turn 180 degrees. That is the same as multiplying by -1. So I is not just a strange mark. It is rotation hidden inside algebra. If I means rotation and E means smooth growth, what does E raised to an imaginary power mean? It means smooth rotation. That is the whole door. The lovely identity is not a trick. It is the moment the blackboard admits that growing in an imaginary direction means moving around a circle. There is a line in math that looks like a prank. It is e to the I pi plus 1 equals 0. 5 marks sit in it. They are e, I, pi, 1, and 0. They look like strangers, yet they land in perfect balance. That small line became the emblem for a wider truth. Math can let growth, shape, motion, and number speak the same tongue. To see why, we need to slow down. We need to meet the cast one by one. Start with 0. 0 is the end of the line. The whole thing falls into 0. In algebra, 0 is where the weights match. If an expression equals 0, the push from one side meets the push from the other. The line comes to rest. Now 1. 1 is the place where we start. Put a point at 1 on the real axis. That is the right edge of the unit circle. The unit circle is the circle with radius 1. It is the home ground for this story. Now pi. Pi is not just the number from circles. Here, it marks a turn. A full turn around the unit circle is 2 pi radians. Half a turn is pi radians. If you start at 1 and turn by pi, you land at -1. Now e. E is about 2.718, but that is not the main thing. E is the base for smooth change. The function e to the x is special. Its rate of change is the function itself. That is why e shows up in growth, decay, compounding, and many rules for motion. Now I. I is the square root of -1. That means I squared equals -1, but it helps to see I as a turn. Multiply by I once, and you turn 90 degrees. Do it again, and you turn to -1. Do it again, and you turn to -I. Do it again, and you are back at 1. The powers of I run in a loop. I to the 0 is 1. I to the 1 is I. I to the 2 is -1. I to the 3 is -I. I to the 4 is 1 again. It is a compass hidden in algebra. Now add one more mark. Call it x. X is the angle. It is the dial on the circle. Let x rise from 0 to pi to 2 pi. The point moves from 1 to -1 and back to 1. Now draw the map. The real axis runs left and right. The imaginary axis runs up and down. The unit circle sits on those axes. The angle x starts from the positive real axis. The point on the circle has a simple name. It is cosine of x plus I sine of x. Here, x is the angle. Why that name? Because the point has two parts. Its horizontal part is cosine of x. Its vertical part is sine of x. In the complex plane, we write a horizontal part plus I times a vertical part. So the point at angle x is cosine of x plus I sine of x. That gives us two ways to speak about the same dot. One way is geometry. The other way is algebra. That is the key. The left side of the board says geometry. The right side says algebra. The trick is that they are naming the same moving point. And once you see that, one question comes next. How can an exponential function name a point on a circle? The famous line is e to the I pi plus 1 equals 0. But the real engine is one step larger. It is e to the I x equals cosine of x plus I sine of x. Here, e is the base of the natural exponential. I is the square root of -1. X is the angle. Cosine of x is the horizontal part of the point on the unit circle. I sine of x is the vertical part written in complex form. This is Euler's formula. Read it slow. E to the ix says this. Take the exponential function. Feed it an imaginary angle. Cosine of x plus I sine of x says this. Go to the point on the unit circle at angle x. Euler's formula says those two things are the same. The exponential is drawing a circle. That is the teacher moment. Start with a dot at 1 on the real axis. Then let x rise. The dot turns around the unit circle. Its horizontal shadow is cosine of x. Its vertical shadow is sine of x. The complex number for the dot is cosine of x plus I sine of x. Now, write another name above that same dot. Write e to the ix. Same dot. Two names. One comes from circular geometry. One comes from exponential algebra. This is why the five strangers can meet. The bridge is not e to the I pi plus 1 equals 0. The bridge is e to the ix equals cosine of x plus I sine of x. The identity is what happens when that bridge reaches half a turn. Now, set x equal to pi. The formula becomes e to the I pi equals cosine of pi plus I sine of pi. Here, e is the base of the natural exponential. I is the square root of -1. Pi is half a turn on the unit circle. Cosine of pi is the horizontal part at that angle. I sine of pi is the vertical part in complex form. On the unit circle, pi means half a turn. Cosine of pi is -1. Sine of pi is 0. So e to the I pi equals -1 plus I times 0. I times 0 is just 0. So e to the I pi equals -1. Add 1 to both sides, you get e to the I pi plus 1 equals 0. Here, e is the base of the natural exponential. I is the square root of -1. Pi is half a turn. 1 is the unit we add to offset -1. 0 is the final balance after the terms cancel. That is the identity. The whole miracle is a half turn. Now we can ask the next hard thing. Why is Euler's formula true at all? There are a few ways to show it. The cleanest path on a blackboard uses power series. A power series builds a function from powers of a number. Start with the exponential. E to the x equals 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus ... Here, e is the base of the natural exponential. X is the input. X squared, x cubed, and the higher powers are repeated multiplication of that input. 2 factorial, 3 factorial, and 4 factorial are the products 2 times 1, 3 times 2 times 1, and 4 times 3 times 2 times 1. Now cosine. Cosine of x equals 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus ... Here, x is the angle. The powers of x are repeated multiplication of that angle. The factorial terms set the size of each piece. Now sine. Sine of x equals x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus ... Here, x is the angle. The odd powers of x are repeated multiplication of that angle. The factorial terms scale each piece. Now take the exponential series and replace x with ix. E to the ix equals 1 plus ix plus open parenthesis ix close parenthesis squared over 2 factorial plus open parenthesis ix close parenthesis cubed over 3 factorial plus open parenthesis ix close parenthesis to the 4th over 4 factorial plus ... Here, e is the base of the natural exponential. I is the square root of -1. X is the angle. The powers of open parenthesis ix close parenthesis are repeated multiplication of that complex input. The factorial terms are the same scaling terms we used above. Now use the cycle of powers of I. I to the 0 is 1. I to the 1 is I. I to the 2 is -1. I to the 3 is -I. I to the 4 is 1 again. So the series changes shape. It becomes 1, then plus ix, then minus x squared over 2 factorial, then minus ix cubed over 3 factorial, then plus x to the 4th over 4 factorial, then plus ix to the 5th over 5 factorial, then minus x to the 6th over 6 factorial, then minus ix to the 7th over 7 factorial, and the pattern goes on. Now, split the terms into two groups. Put the real terms in one pile, put the imaginary terms in another. The real terms are 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on. That is cosine of x. The imaginary terms are I times open parenthesis x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus ... close parenthesis. That is I sine of x. So the whole series becomes e to the ix equals cosine of x plus I sine of x. Here, e is the base of the natural exponential, I is the square root of minus 1, x is the angle, cosine of x is the real part of the point, I sine of x is the imaginary part of the point. This is not a trick. It is the same infinite machine split into two clear parts. One part is the real shadow, one part is the imaginary shadow. Now plug in pi. E to the I pi equals cosine of pi plus I sine of pi. Here, e is the base of the natural exponential. I is the square root of minus 1. Pi is half a turn. Cosine of pi is minus 1. I sine of pi is 0 because sine of pi is 0. Cosine of pi is minus 1. Sine of pi is 0. So e to the I pi equals minus 1. Then e to the I pi plus 1 equals 0. That is the whole path. It can feel too short, but the hard work sat in the translation. An imaginary exponent became circular motion. That was the puzzle. Why could 5 marks that seem to live in different parts of math meet in one neat line? Now we can answer it. E handles smooth change. I turns that change sideways into rotation. Pi picks half a circle. 1 marks the start and the offset. 0 records the exact balance at the end. But there is a wall here. Euler's identity is beautiful. It is easy to say too much about that beauty. It is not a calculator by itself. You do not use e to the I pi plus 1 equals 0 to price a bond. You do not use it by itself to solve a circuit. You do not use it by itself to compress an image. You do not use it by itself to predict a particle. The identity is the postcard. The working machine is Euler's formula. That is, e to the ix equals cosine of x plus I sine of x. The identity is the special case where x equals pi. That difference matters. If someone says the line proves all of reality is one hidden hole, they skip the lesson. The lesson is sharper than that. Analysis, geometry, and algebra can translate into each other. Growth can become rotation. Rotation can become algebra. Waves can become sums of complex exponentials. That is the reusable part. At the start, the 5 constants looked like strangers. The wall is this. The line is not deep because the symbols are famous. It is deep because the structure under them can be used again and again. There is also a hard technical wall. To make Euler's formula strict, you need to know what e to the z means when z is complex. Here, e is the base of the natural exponential. Z is a complex input, not just a real number. You can define it with a power series. You can define it through rules for change. You can define it by extending the function with care into the complex plane. Once that ground is firm, the identity follows cleanly. Without that ground, e to the ix can look like a symbol game. So the honest lesson is plain. Euler's identity is not where the math starts. It is where several deep definitions meet without friction. That is why the line fits on a shirt. That is also why people can spend a lifetime with it. And what do we keep from it? Euler's identity is the clean, special case of Euler's formula, where a half-turn sends the point at 1 to minus 1 and makes e to the I pi plus 1 equals 0. That line became the badge for a larger bridge that now runs through wave math, signal work, quantum theory, and much of modern physics and engineering. The useful move is to look past the famous identity to the machine under it, because e to the ix equals cosine of x plus I sine of x is the part you can use. Now, take the bridge out of the classroom. Euler's identity is the joule. Euler's formula is the engine. The joule is e to the I pi plus 1 equals 0. The engine is e to the I x equals cosine of x plus I sine of x. That engine shows up wherever the world repeats. Sound repeats, electric current repeats, light repeats, radio waves repeat, quantum phases rotate, markets cycle, seasons cycle, machines vibrate. When something repeats, one of the most powerful moves in mathematics is to stop drawing the wave as an up and down squiggle and start seeing it as rotation. That is the trade. In signal processing, a complicated sound can be decomposed into many rotating pieces. Each piece has a frequency. Each piece has an amplitude. Each piece has a phase. Fourier analysis asks a simple question: which rotations are hidden inside this signal? That question is why music can be compressed. It is why noise can be filtered. It is why images can be broken into patterns. It is why wireless communication can separate one channel from another. Euler's formula gives those rotations a clean algebraic form. In electrical engineering, alternating current rises and falls like a sine wave. Engineers often write it as a phasor, which is a rotating complex number. That move turns a time-varying wave into a piece of algebra. Instead of carrying sine and cosine terms through every line, you move into the complex plane, solve the problem there, and translate back. That is not decorative notation. It is a labor-saving machine. In quantum mechanics, complex phase is not optional. The phase of a wave function helps determine how waves interfere. Two paths can reinforce, two paths can cancel. The language e to the I theta is built into that world. Here, theta is an angle. The exponential is not growing away from 0, it is rotating. So, the practical lesson is simple. Whenever you see repetition, ask, what is rotating underneath this? That question turns waves into algebra. It turns vibration into frequency. It turns messy motion into components. It is the useful version of the beauty. The identity itself is small enough to memorize. E to the I pi plus 1 equals 0, but the idea behind it is much larger. The exponential function, the unit circle, imaginary numbers 0 and 1 are not separate islands, they are one coastline. At the beginning, 5 constants looked like strangers. By the end, each one has a job. E brings continuous change. I turns that change sideways. Pi chooses the half turn. 1 marks the starting point. 0 marks the final balance. That is why the line feels so clean. Nothing is extra, nothing is missing. Mathematics connects things that were never supposed to be connectable, and Euler's identity lets you see that connection in one breath.